Hello class 9 students. Today I will talk about real numbers from a different perspective, and we will distinguish between rational numbers and irrational numbers using that perspective. So you will be able to complete your 1.3 exercise in your NCERT book of class 9 for mathematics. So let's get started. So like we had discussed in the previous lecture, so rational numbers are the numbers which can be expressed in the P by Q form. Now, if you look at their expansion, so if I try to do the long division of 10 by 3, what is the pattern that I observe? So, here you can see the remainder that I get is 1 here. Then again, I get a remainder of 1 when I go to the next division. Here again 1. And my recurring decimal of 3 is occurring in the quotient here. Then you look at this, which is another form of P by Q. This terminates. Then you look at 7, division by 7. Here you will see that you get first 3, then 2, then 6, then 4, then 5 remainder, and then you again get 1. As soon as you get 1, you are back to this square 1 and the pattern will start repeating. You will start getting 1, 4, 2, 8, 5, 7 again. Now let's try to understand this pattern. Here, one thing that you need to observe is that the remainder here is constant and the divisor is 3. Here the remainders are 6, 4, 0 and the divisor is 8. Here the remainders repeat after 1, 2, 3, 4, 5, 6. 6 digits, they start repeating. Now, you will observe that remainders either become 0 or they start repeating. So, these are called rational numbers. Whenever your remainders either terminate or after a certain stage they start repeating themselves, then it's a rational number. And you will also observe another thing. Here the repeating string is just one number. It is less than the divisor. Here the number of remainders which are repeating are 6, 1, 2, 3, 4, 5, 6 and it is again less than the divisor 7. So there are two takeaways from this, very important points. So the first takeaway is that the remainder either becomes 0 after a certain stage it starts repeating itself. The second takeaway is that the number of remainders that I have will always be less than the divisor. Now when is the remainder becoming 0? Now let's take examples of terminating numbers. Now, why are they terminating? If you see, if I try to take the prime factorization of this is 5 square. So, we already know, see, if I want to convert this into a decimal, I should be able to do this. Here also, I'll be able to do this. This is already in hundreds. So, here I'll have 7 into 5 to the power 3 upon 10 to the power 3. Here I'll have 2 into 2 to the power 2 upon 10 to the power 2. And this is already 2 upon 10 to the power 2. So such decimals will always be terminating. So if I have my denominator in such a expression where x or y could also be greater than equal to 0, then they are terminating decimals. So this is case 1. The other is when the remainder never becomes 0, but it starts repeating itself. So you will observe even for 7, after 6 digits it starts repeating. So you can write it like this. You put a bar to show that this particular digit is repeating. So if I have 3.572 bar, it means it's 3.5727272. Whatever is repeated, a bar is put on top of that. So 1.27 would mean 1.272727. So such numbers can be expressed as rational numbers. Now how to do it? There's a trick involved, so you need to understand that. Now let's look at these examples first. So suppose there's a rational number given to you. You have to express it in the form of P by Q. So it's simple. Here I have any number given to me. Suppose it's 4.283787. Whatever it is, I will just remove this decimal. And I'm taking it 1, 2, 3, 4, 5, 6 places ahead. So I'll put in 6 zeros here. So this is my P by Q form. So any decimal can be expressed in the form of P by Q as a rational number. Now for this, there's a trick here, like I said. So let's understand this. So suppose I have a number x is equal to 0.3333 and it goes on. So I can simply write it as 0.3 bar. It means 3 is repeating. So only one digit is repeating. So I have to see how many digits are repeating, and accordingly I will multiply this number with 10 to the power those many numbers. So here I'll multiply with 10 to the power 1 into x, which is actually equal to 10x. So it will be 0.33 bar into 10, which effectively means 3 point, because this decimal is going to come here. So it will become 3.3 bar. Now 3.3 bar is actually 3 plus 0.3 bar, and my 0.3 bar is actually x. So my 10x is actually 3 plus x. So it's 9x is equal to 3. X is equal to 3 by 9, which is equal to 1 by 3. And we already know generally that 1 by 3 gives me 0.3 bar. Now let's take another example. So suppose I have x is equal to, so it means it is 1.2727, and it will keep repeating like this. Now how many digits are repeating? 2 digits are repeating. So I'll multiply with 100 here. So 100x, I'll move 2 places here. So 1, 2. So this becomes 127.27 repeating. Now x can be written as 1 plus 0.27 repeating. So this simply means that 0.27 is equal to repeating is equal to x minus 1. I will repeat this here. So this is 127 plus 0.27 repeating. I'll simply put this value 127 plus x minus 1. So 99x, if I take x this side, is equal to 126. X is equal to 126 upon 99. So this is the P by Q form. Let's take another example. X is equal to 0.235, but this is repeating. So it means it is 0.23535, and this keeps repeating. Here again, 2 decimal places are repeating. I will multiply with 100. So 100x is equal to, it's going to go here. So 23.535. Now you can write this as 0.2 plus 0.035. This can be written as 23.5 plus 0.035 repeating, because here if you see, I have separated this and I have figured this out, and this I am getting here also. So from this observation I can say 0.035 with 35 repeating is equal to x minus 0.2. I will put in this value here. So this will give me 23.5 plus x minus 0.2. When I take x on that side, 99x is equal to 23.5 minus 0.2, which is equal to 23.3. So x is equal to 23.3 divided by 99, which is equal to 233 upon 990. So you have to remember that the decimal expansion of a rational number is either terminating, so it terminates like in the first case, or it is non-terminating but recurring. Moreover, a number whose decimal expansion is terminating or non-terminating recurring is rational. So to be able to determine whether a number is rational or not, you can simply expand it. If it is terminating, it is a rational number. If it is non-terminating but recurring, it is again a rational number. And vice versa is true for irrational. You also need to remember, for irrational numbers, square roots of any numbers apart from the numbers which are perfect squares are all irrational numbers. So root 2, root 3, root 4 is not because it's a perfect square, root 9 is not, root 16 is not, but any other square root is always going to be a irrational number. Similarly, pi we had discussed in the last class also. This is an expansion which never terminates, and it does not have a pattern also associated with it. Apart from root 2 and pi, if I want to understand more irrational numbers, anything like this. So here I have 0.1, then 0. I have added 1, 1, then again 0, 1, 1, 1, then again 0, 4 times 1. So anything like this. Maybe 2, 0, 2, 2, 0, 2, 2, 2, 0, 4 times 2. And you could do it with all the digits and you could get an irrational number here. So such irrational numbers, you can see they are non-terminating and non-recurring also, because there is not a particular pattern which is recurring. So let's see this example here. Find an irrational number between 1 by 7 and 2 by 7. Now 1 by 7 by expansion you can find out that it is this. 2 by 7, you can just multiply this answer by 2 and you'll get this answer, because 2 by 7 is effectively 2 into 1 by 7. So you'll be able to get this number. Now, if you want to find out any irrational number between this, so I could take any number which is greater than this and less than this. So here they have taken an example of 0.15, which is actually greater than this and less than this. So here I have written a number 0.15, 015, then 0015. So 15 is repeating here, but you're adding one more 0 here. So I could write 0.160160016 00016 and so on. So any such numbers could be generated and it will be an irrational number. So let's come on to the exercise. Write the following in decimal form and say what kind of decimal expansion it has. So this will be a terminating decimal expansion. You already know, because the denominator is in the power of 2 and 5. This will be recurring. So it is going to be a rational number, but it is recurring, and the number of digits which will repeat will be less than 11. We saw that in 1 by 7 example that we did. Number of digits which were repeating were less than 7. So here the number of digits will be less than 11. This again will be a terminating one. This will be repeating, but the number of digits will be less than 13. Repeating, and this will terminate. So you already are given the value of 1 by 7. You have to predict the values of 2 by 7, 3 by 7 and all these. So it's very easy to do. You already know 1 by 7. 2 by 7 is simply 2 into 1 by 7. 3 into 1 by 7 is 3 by 7. So you can multiply and find out these values. Express the following in the P by Q form. So you have 0.6. Let me do one of them for you. So 0.47. X is equal to 0.4 with 7 repeating. Now only one decimal is repeating, so I will multiply with x. 10 is equal to 4.7 repeating. This could also be written as 4.77 repeating. 4.7 plus 0.07 repeating. So this could be written as 0.4 plus 0.07 repeating. So I could simply say 0.07 repeating is equal to x minus 0.4. So let me replace this here. So this is 4.7 plus x minus 0.4. So this implies 9x. If I take x that side, is equal to 4.3. So x is equal to 4.3 divided by 9, or 43 upon 90. So this is how you can do it. So just try to segregate this recurring number and you'll be able to solve this question whatever form it comes in. I'll do this another one. So x here, x is equal to 0.001 repeating. It means it's 0.001, 001 and so on. Now since there are 3 decimals which are repeating, I will multiply with 1000x and I'll get 1.001 repeating. This is simply equal to 1 plus x. So 999x is equal to 1. So x is equal to 1 upon 999. So I hope this is clear. Express this. So I think you should be able to do this. Why does it make sense? Because it's approximately equal to 1. So it does really make sense. You will see when you do it yourself. What is the maximum number of digits be in a repeating block of digit in the decimal expansion of 1 by 17? So in the example of 1 by 7, we saw that there were 6 digits repeating. Here the maximum number would be 16. And you can perform the division to check your answer. Look at several examples for rational numbers. So they are trying to ask about the 2 to the power x, 5 to the power y property. You should be able to do this now. Write 3 numbers whose decimal expansions are non-terminating, non-recurring. So you could take any examples like this and write them down. All will be correct. Find 3 different irrational numbers between this. So what do? You will expand them. You will write them in their recurring forms. And then you will just find out any one decimal like this. And you will just keep repeating the pattern of 0, adding 2 zeros after the number, then again 3 zeros after the number, and so on. Classify the following numbers as rational or irrational. So root of 23, like I told you, it's not a perfect square, so this is going to be irrational. Perfect square, so rational, because root of 225 is 25. This is obviously a rational number, 3796 divided by 10,000. So here 478 is repeating. This is non-terminating recurring. So that is why it is a rational number. Here 101, this is the same pattern for any irrational number that you see. So this is irrational. So this brings us to the end of this lecture. I will see you in the next one. Thank you.